Now, this is not something you particularly need to know at this stage of your maths, but you might find interesting. I've also tried to make this explanation very simple. You can find lots of stuff on YouTube about different orders of infinity and things like that, but they're actually quite difficult to understand. So I'm going to try and pitch this at a level that an able Year 8 could understand. So it's called Not All Infinities Are Equal. The set of irrational numbers is what is known as an uncountable infinity. The set of rational numbers, whole numbers and fractions, or terminating and recurring decimals, is a countable infinity. To explain what I mean by that, just think of a subset of those rational numbers. Just think about the natural numbers. 1, 2, 3, 4, 5, 6, 7. Yes, you would end up counting an infinite amount of time to get to the end because there is no end. But you can count the actual individual members. So that's a countable infinity. Yeah, you can never really count them all, but they are in principle countable. If you simply choose a single number at random from all possible real numbers, it is more likely to be an irrational number than a rational number. The following thought experiment can explain this, but let me just pause there. We know that there's an infinite number of rational numbers. Indeed, there's an infinite number of just the natural numbers, the counting numbers. There's an infinite number of irrational numbers. But in a sense, and I'm using quote marks here, there are more irrational numbers. So what do I mean by that? So here I've got a 10-sided die and it's numbered 0 to 9. So suppose we have that 10-sided die numbered 0 to 9. We're going to use this die to produce the decimal expansion for a number. Suppose that we have rolled the die 9 times so far, and at this point the result is 0.325325. When we roll the die the next time, we need to roll a 3 to continue the pattern. So the probability that the decimal continues to have a recurrence pattern is 1/10. The probability that the recurrence pattern continues 3 more digits is going to be 1 over 10 cubed, which is 1 in 1,000. In other words, that's producing the next 325, because to produce the 3 is 1/10, then to produce the 2 is 1/10, then to produce the 5 is 1/10, and that's going to continue for the next 325, the next 325 after that, and so on. So at every stage, it's more likely that the recurrence pattern gets broken. The simple fact is that upon any roll, it is always going to be more likely that a recurrence pattern is broken than it being continued. Now, as I said, this is quite a simple treatment, but hopefully it gives you some idea of why there are, in quotes, more irrational numbers than rational numbers. Note, in this context, we can think of terminating decimals as recurring decimals where all of the places are a 0 after a certain point, e.g. 0.125 being 0.125 and then 0 recurring. This is a very simple treatment of this, but hopefully it gives you some idea. Obviously, if you delve into this more, it's very complex.